I would like to welcome you to this 8th lecture on machine learning. Today we will introduce an interesting model called support vector regression and also build up some more ammunition for optimization. So support vector regression will be our next tool to help us avoid overfitting. What is support vector regression? In fact, it adds the family of problems for which we will be able to easily motivate constrained optimization. So far, we have considered the sum of squares error. What does that look like? Well, it's a quadratic function. What is it a quadratic function of? So let's consider the error yi minus w transpose phi of xi. Square this and some overall examples. For the purpose of this graph, we will consider only one example, yi minus w transpose phi xi whole square. So we ignore summation, and we find that more is the deviation of yi from w transpose phi xi. The error grows faster. So you could think of this x-axis as epsilon I centered at 0. What you see on the y-axis is epsilon I square. So basically, any deviation from 0 error is going to be penalized, and it grows fast enough. You could also consider the L1 error. This was the L2 error. The L1 error again is centered at 0, but it grows linearly with deviation of the error. What is this? This is nothing but the absolute value of the difference of the actual value from the predicted value. What we consider in support vector regression is a slightly different model of error, where the error is left 0 within an epsilon band. It increases linearly after the epsilon band, or it could even increase quadratically after the epsilon band. But the point is about giving this margin. This is the epsilon margin of 0 error. So any point in the band of epsilon is not penalized. Thus the loss function is known as epsilon insensitive loss. However, any point outside the band is penalized, and the penalty is different for points above and below the band. So penalty is xi above for points above the band, and it is xi star below the band. So more specifically, what xi and xi star are can be written down as follows. So xi, well, can be written as a max of two different quantities. If indeed yi is greater than w transpose phi xi plus b, then xi is that value. But if yi lies within this band, for example this point, then the error would obviously, the xi would have obviously not be negative, it will be 0. So this is the value of xi I, max of these two quantities. Similarly, xi I star would be the max of W transpose phi xi plus b minus yi and 0. What you ensure in this process is that the support vector regression curve does not necessarily pass through any of the training points. The curve here in black is the SVR curve. Okay, so what is it that we desire? As I said, xi I is max of yi minus W transpose phi of xi minus b and 0. What does this translate to in terms of inequalities? Well, this means that yi minus W transpose phi of xi minus b, well, I think I've need to introduce an epsilon band as well, should be less than equal to epsilon plus xi. Similarly, xi star was max of W transpose phi of xi minus plus b minus yi minus epsilon and 0. This implies that W transpose phi of xi plus b should be less than equal to well, you could include yi here, minus yi should be less than equal to epsilon plus xi star. So these are the constraints we would like to impose. Please keep in mind that by design we would like exactly one of xi and xi star to be non-zero. So it's an exercise for you to indeed verify that this happens. Graphically, this is very intuitive. So here are our expressions, our constraints. Please note that these constraints should hold for all points I. Now coming to the problem that we would like to solve, what is the error? So we could think of the following. We could continue with a regularizer as before, which will correspond to an expression such as norm w square, that's L2 regularizer. What we'll do is scale this by a half, because this is going to help us in optimization steps. This half basically gets cancelled out against the multiple 2 that surfaces when you take the gradient of norm w square, but practically it doesn't matter whether you have a half here or not. What you also need to now consider is the error beyond the margin. Now the error beyond the margin could be xi if it's above or xi star if it's below, but whether the point is above or below is a matter that will be taken care of by the constraints. As far as objective is concerned, we'll just sum up the xi's and the xi stars for each point. This will be an error. What we'll do is add a trade-off factor called C. This is a trade-off factor between the regularizer and the one norm error. So let's write down our optimization problem. So it's minimization over W B xi star 1/2 norm W square plus C times summation over xi and xi star. We have the constraints we wrote earlier. In addition, we need that xi and xi star should be greater than or equal to 0. Please note that these constraints, and especially the objective, because it's a summation over xi and xi star, the objective does encourage negative values of xi and xi star. You can convince yourself that if xi is positive, you might as well have a negative value of xi star in the absence of such a constraint. So the point note is, without this constraint, positivity constraint on xi and xi star, it is possible that xi is greater than 0 and xi star happily tends to a large negative value. Or it's also possible that xi star is positive and xi happily tends to negative value, which actually defeats the whole purpose. We could also have an alternative formulation with 2 norm error and the same L2 regularizer, and this would correspond to a min over WB xi star of 1/2 norm W square. But now we will have squared deviations from the epsilon band. This is the 2 norm error that we're talking about here. The constraints will remain the same. With a small difference. So you don't need these constraints of positivity on xi and xi star. The reason is that negative xi and xi star will also lead to increased values of objective because of the square term, and as such the constraints are hard enough to satisfy for small positive values of xi and xi star. So why would you even want these i's to be negative? It just becomes harder to satisfy those constraints, and the objective isn't happy either. So the constraints xi and xi star are not necessary, they are implicit. So far we have seen several optimization problems: the unconstrained optimization problem with a penalty given by omega w. You could also put the constraint within penalty within a constraint and call it constraint regularization. What we have considered now is support vector regression, 2 formulations, L1 error and L2 error. We need to seriously look at optimization tools to be able to solve all these problems. In fact, we will also make use of optimization to show that the 2 formulations, unconstrained or penalized unconstrained, and the constrained version with the penalty sitting in the constraint, are equivalent in some sense, which means for every choice of lambda there is a corresponding theta in the constraint version, and for every choice of theta there is a corresponding lambda in the penalized version. What we also want to do is develop something called the dual of the support vector regression problem, which opens up an entire new world of possibilities. The dual of the support vector regression is an equivalent optimization problem, a problem equivalent to the original optimization problem we just formulated. We will also call this original problem the primal optimization problem. So the dual of the primal formulation is supposed to be equivalent, but gives you handle into something called kernels. But for all this we will need to build up optimization. I'd also bring to your attention an important point that somehow for the unconstrained optimization problem of least squares linear regression, we were able to get a closed form solution, and the intuition is you could get that solution by setting the gradient or the derivative, which is a special case of the gradient, to 0. Basically the rate of change of the function at the point of minimum should be 0, and we can hope that we find a closed form solution in general. We can infer a closed form solution for the case of least squares linear regression, but then there are many other questions. When is it a minimum, when is it a global minimum? And in fact for most optimization problems, finding closed form solutions is very difficult. So are there alternative methods? So for example, even with linear regression with least square objective, the inverse matrix which we see here might be difficult to compute, especially if phi is very large matrix. So can we avoid closed form solution and develop iterative methods even for such settings? More about this in the following.